Hello everybody. Now we're going to discuss this term in the equation, which is the summation of forces. And in this video, we're going to discuss the most common forces that we face or we deal with in our problems. And we will categorize them to make it easy for us to know what are the forces that we are going to see in our systems. So the forces can be categorized into two types or two categories of forces. One, what we call the body forces, and these are the forces that are acting on the whole body. It's not only the outer surface; it's acting on the whole body. This is like the gravitational force, or this is the most or the only type that we're going to discuss here or consider here, which is the gravitational force, which is the weight of the fluid or weight of the system or the control volume. Just to be more precise, it's the weight of the control volume. And it always, of course, it acts downwards. There are other types of body forces like the magnetic forces, but we don't consider these here. They're not of interest for us here. So this is the first type. The second type is the force or the type of forces that act on the surface of the control volume, and this is what we call the surface forces. And they include the forces due to and again, just to make this point clear, what we mean by surface forces, that they act on the surface, meaning that they don't act on the whole control surface, they just act on the surface. By the surface of the control volume is if we have this is our system and this is the control volume, so we mean the forces acting on the red dotted or dashed line. This is what we mean by the surface forces. So they don't act on the inner surface or the inner or the inner components of the control surface control volume. They act on the outer surface of the control volume. And we can have different categories. The most common are the flow pressure, or the forces due to the pressure of the flow, the viscous forces, and which are the friction forces, and the reaction forces. The flow pressure is, we know that if we have, let's say, a flow that or liquid that's flowing in this direction, so it's flowing with a pressure. So this pressure, there is a force that results due to this pressure, which is going to be the pressure times the area. So this is what we call the pressure times area. This is the force due to this pressure. Okay, the viscous forces, we are not going to include it here, but if we have part of the control surface that includes friction of the fluid with the control surface, it's mainly if the control surface is parallel to the flow of the fluid. And we will go through this in a slide or two. Then this is one of the forces that we should include. The reaction is, and let's say we have this body that we are interested in is like sitting on the ground or placed on the ground. Then of course there is weight acting downward, and there is also a reaction force from the ground on the body, and that's why it doesn't penetrate the ground. The ground is acting with a force in the opposite direction. So this is what we call a reaction force. There will be also reaction forces if there is a hinge or there is a bolt that's holding this this body. Then there is a reaction force acting upward, because it prevents the body from going downward. So it's mainly in the direction opposite to the other forces. So if the force is gravitational force, then the reaction is going to be upward. If, let's say, we have something that will fall to the right, then the forces would be to the left. So it's an opposite force. Yeah, this is the reaction force. So we can say that some of the forces is the body forces, some of body forces, and some of the surface forces. And to be more detailed, the gravitational forces are the body forces. The surface forces are due to the pressure, the viscous forces, and the reaction forces. We will go through them in more details, or they will be more clear when we solve problems after two videos. But for now, these are the types of forces that we should take into account when we do the analysis on the control volume and see what are the forces acting them. It's important to understand what we mean by surface forces and what we mean by body forces. So the difference is important. So you don't include a force in the wrong place. So there are a couple of things we need to I want to make clear regarding the pressure. So one thing which is a very good simplification that we can do regarding the pressure forces is, or the forces due to the pressure, is using the absolute or gauge pressure. So let's say, for instance, we have a body like this. So it has 4 sides, and there are, of course, it's under atmospheric conditions, and there is a force on one side, while the other forces, or the other surface, the other sides, are exposed to the atmospheric pressure. So if we are going to do the analysis for the surface forces, we have force acting on the surface and force acting on the surface, and for all the 4 surfaces are exposed to the forces. The 3 surfaces are exposed to forces due to the pressure, and this is due to the atmospheric pressure, and this is the atmospheric pressure plus the pressure of the fluid. Okay, if there's the fluid flowing inside, then this is the pressure of the fluid. So you have to do the analysis for surface forces on 4 surfaces, which is going to be a very, very time-consuming thing. However, if we do the analysis using the gauge pressure instead of atmospheric pressure, so here it's atmospheric pressure, then the gauge pressure on these 3 sides is going to be 0. And actually, this is a very, very good simplification, because the forces will cancel out. If we have atmospheric pressure in this direction, they will cancel out. In this direction will cancel out. So it's more convenient and more easier to go for the gauge pressure. And this is, again, we do all our calculations under atmospheric conditions. So everything would be exposed to atmospheric pressure. All the surfaces will be exposed to atmospheric pressure. The surfaces that are not exposed to the fluid flow, if there is no fluid flow on a specific surface. So in this case, we'll have only one force that we are going to consider, while the other forces would be 0, which is going to be a very, very good, it's not simplification, but it's a good way of simplifying the calculations. It's not simplification of the equations. The equations are still the same, but we are putting 0 terms instead of including them. So this is the first point. The second point, it's an important point, which is the pressure forces on the control volume. So let's say we have a pipe where fluid is flowing with flow inside from this direction. This is the inner flow with pressure P in, and there is the outer flow on the right side with the pressure P out. And we want to write the expression for the forces acting on the control surface. Again, the control surface is this red dotted dashed rectangle. So the parts of it exposed to the fluid is this inlet and this outlet. Okay, this black line is not part of, or the pipes of the wall are not part of the control surface. So we don't include any forces on these black lines, or the walls of the pipe. So we proved that so this is what we're going to do. So we will only include the pressure inner and the outer pressure in the control volume. So the forces, we know that the forces are going to be the pressure times the area. So this is not a big deal. The question here is, what is the direction of these forces? And this is a very important point. There's a point that needs to be clear in your mind, that we are interested in the forces acting on the control volume. Okay, it's the forces acting on the control volume. This point is not clear in the textbook, so I want to make it clear to clarify why we do the calculations this way. So we are interested in what acts on the control volume from this side and what acts on the control volume on this side. So for what we know from before in chapter 3, that we made the derivation and we proved that the pressure is a scalar quantity, which means that it doesn't have any specific direction, which means that at a specific point the force or the pressure is acting in all directions at a specific point, in all directions in the same quantity. So if we have a fluid at the entrance here, then the pressure of this fluid produces forces in all directions with the same quantity. So we are interested in the forces acting on the control volume. So we say that the force is going to be in this direction, because this is the direction of the force at this point acting on the control volume, which is going to be in this direction. Of course, there are forces acting backward and acting in different angles, but it's not on the control volume, so I don't care about them. I just care about what acts on the control volume. And this is very intuitive, because you know the flow is going in this direction, so we assume that the pressure will be in the same, or the force is going to be in the same direction of the flow. While on the other side, and this is the part that's counterintuitive, that if we are interested in the forces on this side, then again we are interested in the forces acting on the control volume. So we know the pressure at the outlet. So we know the pressure here at the right side of the control volume. So in this case, it's the same thing here that we said before, that there are forces or the pressure acting in all directions, so there will be forces acting outward and acting inward. If we include the forces acting outward, then this is a force that is acting on something else, not the control volume. So it's acting on what we have here, which is not the control volume that we are interested in. So the force that's acting in the control volume will be in this direction. Okay, although the flow is going in this direction, but again we said that the pressure is a scalar quantity, so it doesn't have a specific direction, so it will generate forces in all directions. So we are interested in the component of the force that's acting on the control volume, not the force with the direction of the flow. So that's why for the pressure forces, we are including the pressure forces always acting towards the control volume. This is a very important point to include. So I hope it's clear now, because as I said, it's not clarified in the textbook. There is one last thing about the control volume choice, which is a very important thing. As we said before in the last video, that the choice of the control volume is very important, because this is what will dictate the type of forces that we include in our calculations, and what we will include and what we will not include. So in this example here, we have a faucet that is fitted to the wall with bolts, and there is a flow that's going in and flow that's going out of the faucet, and you'd see there is this valve that opens and closes this faucet. So we have one of two options: either to do the calculations on the control volume A, which is the dashed purple line here, or to include it, or to do the equations, or write the equations on the control volume B, which is the red dashed line. So in both cases we have a control volume that includes the fluid. So we have here the fluid that is inside the faucet, but the difference is what are the types of forces we are going to include. So if we include the control volume A, then we have the inlet and outlet forces due to the pressure. So we have pressure in this direction and pressure in this direction, and it's going to be the same for control volume B, because it's this part and this part is common part of the control volumes, or the two control volumes. But for the control volume A, we need to include the viscous forces, which is the friction between the fluid and the walls of the inner walls of the faucet. It's going to be very complicated, because in this case we need to know the geometry of the faucet from inside, the type of material that's used, the how much losses or the friction we have, which is a very, very complex thing. While if we do the, and of course for this is for the surface forces. For the body forces, we include the weight of the faucet and the water inside it. While if we, I mean that's just the water on the faucet. While if we include or do the calculations on the red control volume, which is the control volume B, we will only include, of course, the weight, the body forces will include both the water and the faucet, which is, body forces are easy to calculate. But in this case, the surface forces will be only for the pressure forces here and here, and we are not including this because this is not part of the surface. The surface again is the red dashed line. So in this case, the fluid is only acting on this part and on this part, and not on the inner walls, or we don't include the inner walls because they are not part of the control surface. So the choice of the control surface is a very, very important thing. It can simplify the equation or the calculations very much, or it can complicate the calculations very much. So we have to be very careful when we choose the control volume. I'm going to stop here, and in the next video we are going to discuss the special cases of the equation. the linear momentum equation that we are going to use in our calculations in the future. So I'll see you then, inshallah. Goodbye.